Hello RubyConf. I'm Peter, and I'm a Ruby core committer and senior developer at Shopify in the Ruby infrastructure team.
And I'm Matt. I'm also at Shopify, and I'm also a senior developer in the Ruby infrastructure team.
For the past year, we've been working together to make some improvements to how memory is laid out in Ruby.
In this talk, we're going to summarize the work that we've done so far, the challenges that we've faced, and where we're heading in the future.
But before we can go into detail, we're going to provide some background on how Ruby's garbage collector structures and manages memory.
When we create an object in Ruby, the interpreter stores a data structure called an RVALUE in memory to hold it. An RVALUE is always 40 bytes wide, and it contains a union of different data structures that represent all the possible Ruby core types. So we could have a struct representing a string, or an array, or a class, and so on. And each one of these types contain their own fields and data structures specific to that type. The RVALUE itself is just a container for our Ruby objects. Let's look more closely at one of Ruby's object types, RClass in this case. The first 16 bytes of every type are always the same, an 8-byte field called flags, followed by an 8-byte pointer to the class of the object. The remaining 24 bytes are different for every type. RClass objects store a pointer to an extension object here. Strings can store the actual string content, and so on. These RVALUEs are organized into regions called pages. A heap page is a 16 kilobyte memory region. Each page has a maximum of 409 slots, where each slot can hold one RVALUE. A heap page's memory region is always contiguous. The slots have memory addresses that are 40 bytes apart with no gaps between them. Initially, when the heap page is created, all the slots will be filled with an internal type called t_none. This type represents an empty slot. It contains only flags and a pointer value called next that can point to an RVALUE. This allows these empty slots to be linked together to form a data structure called the freelist. When a heap page is initialized, Ruby walks up each page, visiting each slot in turn. As we arrive at each slot, we set a pointer on the heap page, called the freelist pointer, to the address of that slot, and then set the slot's next pointer to the address of the previous slot we visited. This creates a singly linked list of empty slots. When we need to allocate an object, and we need an empty slot, Ruby asks the heap page for the first slot on the freelist. The heap page returns the slot, and then the freelist pointer is updated to point at the next slot in the list. This unlinks our slot from the freelist, allowing us to put data in it. The use of a freelist means that this part of object allocation is both fast and a constant time operation, even when a page is sparsely populated. Because if the page has at least one empty slot, the freelist is guaranteed to always point to it. But eventually, our heap pages are going to run out of slots, and this is where the garbage collector is required. If the freelist is empty when Ruby tries to allocate into the page, it must mean that there are no free slots left on that page. So now Peter's going to talk about how and when the garbage collector runs to release objects that are no longer necessary. Over to you, Peter.
Now that we've looked at how memory is laid out inside Ruby, let's look at how Ruby's garbage collector works. Ruby's garbage collection phase consists of 3 distinct phases: marking, sweeping, and compaction. The last phase, compaction, is optional and does not run unless manually enabled. Ruby's garbage collection is stop the world, meaning that Ruby code is not executed when the garbage collector is active. The garbage collector in Ruby is fairly complex, so we can't possibly cover all the technical details in just a few minutes, but we'll provide a very high-level overview that contains all the information you will need to know for this talk. Let's first look at marking. Marking is the phase where we determine which Ruby objects are alive and which ones can be freed. We first mark the roots, which include things like global variables, classes, modules, and constants. We then perform breadth-first search to traverse the network of live objects. Let's see an example of this. Here's a toy example of a heap with 2 pages with 7 slots on each page. We have a total of 10 objects labeled A through J. Slots with no label means that the slot is empty. The arrows indicate references. For example, the arrow from object J to object D means that object J holds a reference to object D. Examples of references could be the contents of arrays or instance variables of objects. The first step of marking requires us to mark the root objects. The root objects here are objects A and B. Let's now mark these 2 objects. From A and B, objects C and G are reachable, and not marked, so we mark them. Then from objects C and G, objects F and H are reachable and not marked, so we mark them. Objects F and H do not refer to any unmarked objects. Since we did not mark any objects in this step, it means that marking is complete. Now that we finish marking, all marked objects are live objects, and all unmarked objects are dead and can be reclaimed by the garbage collector. We can simply scan the slots on the pages and free the ones that are not marked. Let's continue to use the example we used for marking. Here we move our cursor to the first object in the page that is not marked, object D in this case. We can free the object and reclaim the memory. We then continue to move the cursor until we reach the next unmarked object, which is object E. We've reached the end of page 1, so let's move to sweep page 2. Again, we move the cursor until the first unmarked object is reached and will free object I. We can continue to move the cursor until we reach the next unmarked object, which is object J. Now that we've swept all the pages, sweeping is complete. Manual compaction was a new feature introduced in Ruby 2.7 and further improved with automatic compaction in Ruby 3.0. However, this feature remains optional and is turned off by default. Compaction moves objects within the heap to the start of the heap. This has several benefits, including reduced memory usage, faster garbage collection, and better copy on write performance. Ruby uses the two-finger algorithm for compaction, which I will explain in more detail. The compaction algorithm involves two steps, the compact step and the reference updating step. The compact step moves objects from the end of the heap to the start of the heap. When this step completes, we do the reference updating step. In this step, we scan all the objects and update the pointers that have moved. Let's see an example of compaction in action. The last live object of the heap is object H, and the first empty slot in the heap is slot 1. So we moved object H to slot 1 and leave a forwarding address. This forwarding address will tell us where the object was moved to. We will use this forwarding address in the reference updating step. We moved object G to slot 4 and leave a forwarding address. We move object F to slot 5 and leave a forwarding address. We are now done the compact step because there are no more objects to move. But we're not done yet. We must do the reference updating step. Let's say our object references look like this, where the arrows indicate that a particular object refers to another object. We need to check the references of each object and update the reference if it points to a forwarding address. Here, object B has one reference to forwarding addresses. By reading the forwarding address, we can update this reference to the correct one, which is object H. Next, we see that object C holds two references to moved objects. We can update the references of object C to point to the correct ones. Now that we have updated all the references, we can claim these forwarding addresses since we don't need them anymore. We'll reclaim slots 7, 8, and 11. So that's how the garbage collector works. But throughout this talk, we've been referring to slots as always being a fixed size. And Matt's going to talk about how we handle the case where the object needs to store additional data.
So as we heard, Ruby objects aren't always a fixed size. There are two scenarios to consider. When the object fits in the 24 bytes at the end of an RVALUE, and when they don't. We'll look at two strings, hello world, which is 12 bytes, and hello RubyConf, thanks for having us, which is 36 bytes. When we allocate the string, Ruby checks the requested string length against an internal constant called rstring_embed_len_max. And if the requested length is shorter than rstring_embed_len_max, which it is in this case, it just pushes the string data straight into the remainder of the slot after the flags. When the string length is longer than rstring_embed_len_max, Ruby sets a bit on the RVALUE's flags called the noEmbed bit. This signifies that the data inside the RVALUE is not the actual string, but a pointer to a separately allocated memory region. It then uses malloc to reserve a new memory region outside of the existing heap. It stores the address to that memory in the 24 bytes of the RVALUE after the flags and class, and copies the string data into that newly malloced memory. And with that, we've looked at the main ways Ruby stores objects in memory. So now, Peter's going to talk about some of the challenges with a memory layout like this and introduce our project, Variable Width Allocation, which is attempting to fix them.
Let's discuss some bottlenecks that exist within the Ruby heap that we aim to tackle with this project. The first issue is that a Ruby object often requires multiple pieces of memory to store data. You've just seen an example of this with the string example, where the contents of the string exist in a separate location than the string object itself. This results in poor cache locality. Additionally, this memory is often acquired through the system using malloc, which has a performance impact. We often think that the CPU only has a single level of memory, but that's not true. In order to improve performance, there's faster memory built onto the CPU itself called caches. These caches are further divided into multiple levels, usually 3 levels. The lower level the cache, the closer the cache is to the CPU core. By being closer, the electric signal travels a shorter distance, so it has better performance. Let's talk a little bit about how CPU caches work. Whenever a piece of memory is fetched from main memory, it is also stored in the CPU caches. It's important to note that data is fetched from main memory in units of cache lines, which on the x86 architecture found in Intel and AMD CPUs is 64 bytes. What this means is that even if you need just a single byte of data, all 64 bytes is fetched for you. When the CPU cache is full, it will overwrite the least recently used data to make space for the most recently accessed data. Two terms that is used is cache hit for when a piece of data we access exists in the CPU cache, so we don't need to access the main memory, and conversely, a cache miss is when the data does not exist in any caches, so we need to do a very slow read from the main memory. As you might expect, a very important metric for optimizing performance is to increase the cache hit rate, so we need to read from the slow main memory less frequently. Let's see the cache performance of the current Ruby implementation. Let's use the example of an array. In the current implementation, the array points to a region of memory in the system heap, acquired through malloc to store the contents. Our array has 4 elements, so we need 4 pointers to Ruby objects. Since each pointer is 8 bytes on the 64-bit system, we need 32 bytes of memory. The object occupies one RVALUE, which is 40 bytes, and the content occupies 32 bytes. In order to read the elements of this array, we must do 2 memory fetches to fetch 2 cache lines. Acquiring memory from the system heap using malloc is not free. It comes with performance overhead, so we want to minimize the number of times we call malloc. Malloc also requires space for headers that store metadata when allocating memory, which may add up and result in increased memory usage. We're not the first ones trying to tackle this particular issue. Ruby 2.6 introduced a second heap into Ruby called the transient heap that aims to speed up Ruby by reducing the number of malloc calls. It was successful in improving performance, and some benchmarks saw performance improvement by up to 50%. However, the transient heap has technical limitations and cannot be a true malloc replacement. One of the major goals of this project is to improve the overall performance of Ruby by letting Ruby control its memory layout rather than calling the malloc system library and relying on the system to manage memory. Since Ruby's garbage collector is aware of the memory structure of each type of object, it can optimize for faster allocation and for better efficiency. By placing the contents of the object right after the object itself, we can improve cache locality. By allocating dynamic sized memory inside the Ruby garbage collector, we can avoid malloc system calls and thus be able to improve performance. Now, let's look at how the memory layout changes when we use variable width allocation. Here we see the array example again. What this project aims to do is to move the array's data from the system heap to the Ruby heap right after the object itself. So what does this accomplish for us? Well, we remove the need to do a malloc system call when creating the array object. Let's see if we improve cache performance. Again, recall that every Ruby object requires allocating a RVALUE, which is 40 bytes in size. Our array data itself is 32 bytes. By placing the contents of the array right next to the array object itself, we can now access the first 3 elements of the array while remaining in the same cache line.
So far, we've merged 2 major iterations into Ruby, and our third is open for feedback now. In our first 2 pull requests, we built the infrastructure required to move data that would previously have been allocated on the system heap into a heap page alongside the RVALUE it's attached to, and we provided a reference implementation in RClass. The changes up until now have been minimally intrusive, as this feature was turned off by default and required recompiling with a compile time flag to enable it. In our latest pull request, we've implemented a variable width allocation for strings, and additionally, because we're confident about the stability and the performance of variable width allocation, We've also proposed to turn it on by default. We'll talk more about the performance results later in this talk.
Now let's walk through an example of what this work does so far. We're going to talk about class allocation. These two scenarios allocate R values containing R class objects. A class has data that's attached to it, its instance methods, instance variables, and so on. So Ruby creates a separate data structure for this called RBClass EXTT. It's a fixed size of 104 bytes allocated on the system heap. This is what the current allocation code looks like that's not using variable width allocation. We first acquire a R value from the garbage collector using new obj_of. Then we allocate a region for the RBClass EXTT struct using zalloc, which we'll call malloc to acquire memory. This is what the class allocation code looks like when using variable width allocation. First thing that stands out is that we're calling a different new obj entry point, and this one takes an allocation size. This is the size in bytes of the slot that we wish to allocate from the garbage collector, so 40 bytes for the R value and 104 bytes for the RBClass EXTT struct, which is 144 bytes in total. The garbage collector is guaranteed to allocate a slot that is at least the requested size, but may allocate a slot that is larger than the requested size. We will see the reason for this soon. You've just seen the API to allocate classes to variable width allocation, but how does it all work? Let's take a closer look inside the garbage collector. Remember that Ruby's memory heap is divided into pages, and each page is made up of 40 byte slots. We've changed the heap to support pages that contain different size slots. To do this, we've introduced a new structure called a size pool. Pages within the size pool have a particular slot size. The slot size is a power of 2 multiple of R value size. So, 40 bytes, 80 bytes, 160 bytes, 320 bytes, and so on. We chose powers of 2 multiples because they're easiest to work with and efficient, since we can use bit shift operations to calculate them. We use multiples of R value size so we don't waste space when allocating a single R value of space, since all objects that don't use variable width allocation will only allocate a single R value worth of space. Here, we see a diagram with 4 size pools, and their page slot sizes are labeled. Now, we want to allocate a class object. We first need to calculate the size pool which we're allocating into. A class object will need 144 bytes of space, 40 bytes for the object, and 104 bytes for the RBClass EXTT struct. This is 3.6 R values wide, which is rounded up to the next power of 2, so it will require 4 R values worth of space, or on the third size pool. Let's zoom into this size pool. Each size pool has its own pool of pages and holds a free list. When we want to allocate, we just allocate into the head of the free list and then move the free list pointer to the next element in the linked list. Now let's allocate our class object into the free slot. We allocate both the class R value and the RBClass EXTT struct into the same slot. Of course, we waste about 16 bytes at the end because we only used 144 bytes and the slot is 160 bytes wide. So that's how an object of dynamic size is allocated using variable width allocation.
In our latest pull request, we implemented variable width allocation for strings. However, unlike classes which only allocate a fixed size data structure, strings are malleable and can change sizes, and this makes them more challenging to deal with. Earlier in this talk, we spoke about the 2 types of Ruby strings. Shorter, embedded strings, where the string content is stored directly in the R value itself, and longer strings that have their content separately allocated using malloc and have just a reference stored in the R value. Prior to variable width allocation, only strings shorter than 24 bytes could be embedded. As part of this project, we changed string allocation to enable longer length strings to be embedded. So let's look at allocating our example strings again with variable width allocation and see what's changed. Our first string, hello world, was embeddable before variable width allocation, and this is still the case. We allocate the headers, the flags, and the class as normal, and then push the string content in directly after them. Those with a keen eye may notice that the string headers are now 18 bytes instead of 16. This is because strings allocated using variable width allocation have to support a longer embed length, and so we need a couple of extra bytes to store this larger number. So the headers now occupy 18 bytes, and the contents occupy 12 bytes, which means we need 30 bytes in total. This fits inside the slots of our first size pool, which are 40 bytes, so we request a free slot and allocate into it, with 10 bytes at the end of the slot going unused. Now let's look at allocating our longer example string. Remember that before variable width allocation, this string was too long to be embedded, so the contents were allocated externally using malloc. Now, this string can also be embedded. The string contents are 36 bytes, and the headers are 18 bytes, so this string requires a total of 54 bytes. The second size pool is the smallest pool into which this string fits, as it has a slot size of 80 bytes. So we allocate into a free slot from this pool, and 26 bytes go unused at the end of the slot. But what happens if we try to resize a string? For example, what if we tried to double this string by appending it to itself? The string's going to become too long to fit in the slot. Currently, we don't have a great way to handle this, so we fall back to allocating the contents outside of the Ruby heap, just as we would have done before VWA was implemented. To convert this embedded string to a no-embed string, we first allocate memory for the new string contents using malloc. Then we convert the rstring headers to use the original 40-byte rstring structure, and we set the no-embed bit in the flags. Finally, we set the string's data pointer to point to the region we just allocated. Now, our string object is exactly the same as if it had been allocated prior to variable width allocation being implemented. However, this fallback solution does mean that any space past 40 bytes is wasted. So as this is allocated in an 80-byte slot, resizing this string wastes 40 bytes. We don't have a way to deal with this yet, but we do have some ideas, and we're going to discuss those later on in this talk. And benchmarks of memory performance have shown that this is not a very significant issue for the workloads we tested. Now, Peter's going to tell you about our benchmarks, and talk about how we're measuring runtime and memory performance throughout this project.
We deployed variable width allocation and the corresponding commit on the Ruby master branch on a small portion of production traffic of a Shopify service. We collected data over 1 day, where they each served around 84 million requests. We did not see a change in response times beyond the margin of error. We looked at average, 50th percentile, 90th percentile, and 99th percentile response times. However, variable width allocation did decrease memory usage by about 4%. Synthetic benchmarks were ran on a bare metal Ubuntu machine on AWS. Railsbench and rdoc generation was benchmarked using the glibc and malloc allocators. glibc and malloc are implementations of the C library function called malloc used to allocate memory. Different allocators are implemented differently, and so they have different properties. glibc is the default allocator in Ubuntu. If you're interested in looking at more in-depth results and analysis, check out the ticket linked in the slides. In Railsbench, we see a slight increase in memory usage when using glibc and no increase when using malloc. However, we also see a small performance increase for both glibc and malloc. This graph graphs the RSS, or resident set size, which is the amount of memory held in RAM. We ran the two branches 25 times each, and each run consists of 20,000 requests. The graph graphs the memory usage over time. Variable width allocation is graphed in green, and the master branch is graphed in blue. rdoc generation generates the Ruby documentation. Unlike Railsbench, where variable width allocation used more memory, here we see significantly lower memory usage for a slight reduction in performance. You can see in this graph that the branch uses significantly lower memory. We wrote some microbenchmarks to highlight the performance increase of variable width allocation. For these benchmarks, we use 71-byte strings, which is embedded when using variable width allocation, and not embedded when not using variable width allocation. Our benchmark results show that comparing two strings is 35% faster. The times method also benchmarks allocation speed and is 15% faster. Similarly, setting a character in the string is also 15% faster. This clearly shows the performance benefits of using variable width allocation. We're confident about the stability of variable width allocation. Variable width allocation passes all tests on CI on Shopify's Rails monolith, and we ran it for a small portion of production traffic of a Shopify service for a week, where it served over 500 million requests. We also believe that the benchmark results are satisfactory. So in the latest patch, we propose that variable width allocation is enabled by default. At the time of recording this talk, this proposal is open for feedback. However, it's likely that it has undergone changes and perhaps even merged, so please check the ticket linked in the slides for the most up-to-date information. Now that you've seen our current implementation and some performance results, Matt will now talk about some limitations of this implementation and how we're planning on tackling them.
The first issue to talk about is increasing coverage. Currently, only classes and strings are taking advantage of the benefits of VWA. In order to see an even larger performance improvements, we need to have as many object types as possible using it. Next up is resizing. As you saw in our string implementation, we don't currently have an elegant way to resize objects. This is a tough problem, and solving it's one of our next major milestones. An idea we're currently investigating is to leverage GC compaction to move object data for us. So, when we need to resize up and the current slot is not large enough, we could allocate the new data into a slot in a larger size pool, and then use compaction to move the original object structure next to its data again and free up the old slot. One other thing that we'd like to do eventually is to shrink the size of the RVALUE struct from 40 bytes down to 32 bytes. We want to do this because it means that slots in the heap page will then be aligned on CPU cache lines. For example, in the diagram below, we can see that many of the 40-byte slots straddle two cache lines, and so reading a single slot requires two potentially expensive cache lookups. If the slot size was shrunk to 32 bytes, all the slots become aligned on cache lines, and reading a slot never requires more than one cache lookup. This isn't something we can do right now, as too many objects are still using all 40 bytes of the RVALUE, so they'd end up being allocated into a 64-byte slot or larger, and then wasting 24 bytes or more. Overall, we're proud of the progress that we've made, but we still have a long way to go, and many things to explore. We plan on to share progress updates with the community frequently, via conference talks and blog posts. But for now, the best way to keep an eye on what we're up to is the Shopify Ruby fork on GitHub and the Ruby core bug tracker.
And that's it, folks. In this talk, we looked at how Ruby's memory allocator and garbage collector works, some of the issues in Ruby's memory layout, how we're trying to solve them with variable width allocation, as well as our current progress in the project.
We're continuing to improve the implementation, and we still have a long way to go. Thanks for listening, and thanks to RubyConf for having us.